I don't know. It's unclassified now, whatever it is. I'm not sure what this is. The very early portable modem. Wow. CRT. Very early CRT. Some semi-secret notes. Okay. Okay, when you get something like this, right? Let me see.
Dragons?
I'm finally going to say something like this. The main problem was fictions on it. They got unaware of fading. So someday
Some kind of black box. Ooh. Storage manual. Some old cards. I forgot how they are now. Of course, that famous core memory. And, excuse me, I just want to get this on video, no problem. We'll get you right in there again.
It's hard to see those little donuts from there.
Yeah, I know. Let's get close. It's not focusing. Is that your wide angle there?
Yeah, pretty much.
I'm going to have to get some lenses for this. I get some I saw that.
I'm Peter Nerdsey from Sun Microsystems. So I arranged this program along with Gene Frankel, also from Sun. And the background is that I live in Santa Cruz, a couple of blocks away from Harry Husky, who's a real pioneer and veteran of the computer industry. Harry built the first computer ever built in California, the SPAC in Los Angeles for the Bureau of Standards. And then he went on to build the first, what's been called the first personal computer, or the first engineering workstation, Bendix G15, which was the first computer ever sold for individual use by individual engineers. And Harry lives a couple of blocks from me in Santa Cruz. I kept running across his name in history books. And then I thought I'd like to hear his story, and I thought people at Sun would be interested, so we had him talk at Sun at the end of December last year. And he talked about his experiences. He worked for Alan Turing, for example, for a year in England. He went on to build these machines, and he went on to a career of teaching computer science at Berkeley, UCSC, also UCLA. And there was a good deal of interest there at Sun in Harry's talk, which prompted me to think of a series about computer history talks. Jeannie was ready to join me in organizing this series. So this will be the first talk, and we have one scheduled for May 25th, again, Tuesday evening. The location we don't have settled yet. We have a room in Sun that's at this point ungeared, and the room will be announced in the Mercury News computing calendar the weekend before, if you don't see it on email. And for that talk, we have Bob Metcalf and David Boggs and Ron Crane, who, the three of them, pretty much defined the early history of Ethernet, along with Robert Garner from Sun, maybe working as a moderator in that discussion. And then this fall in September, a talk by the Bank of America on OMA, which was the project which first was able to electronically process checks. The numbers you see at the bottom of your checks today were defined there in the OMA project at Bank of America back in 1956. And you'll see that flyer out on the table in the hall about a computer history open house, and that's May 21st, just before the May program, both at Computer Museum at Livermore and also Bank of America Technology Center in Concord. The Computer Museum will be open from 1 to 3 that afternoon, and the Technology Center exhibit from 3 to 5. So come visit the Computer Museum and then go on to Concord and see the exhibit. And let's say that in my researches so far, it seems like Lawrence Livermore Laboratory and Bank of America, two of the local computer users, have made the most serious effort to record and preserve computer history. I think it's important to everybody working in the computer industry to be aware of history, because it's too often happens people don't record or preserve the history, and then you're in the situation of repeating your old mistakes. It's true, you know, learn from history, doomed to repeat it. The computer industry has this failing of being always forward-oriented, progressive, and that can lead you to not learn the lessons of the past. Having said that, I'll turn the program now over to John Ranaletti, who is Barbara Costello, who's here this evening, founded the Computer Museum of Livermore 15 years ago, and John will introduce the panel.
Thank you, Peter. We're happy to be here. It's rather a sobering fact in life that one sees things that you felt like you worked on yesterday in the museum. That's the way technology moves around here. I'd like to introduce our panel, starting with the person on your left, is Norm Hardy. 1963, Norm was concerned mostly with a 6600 time-sharing system that was about to arrive. He was instrumental in doing implementation of our first time-sharing system called GOB, G-O-B, which stood for Generous Omnipotent Benefactor. He also makes as a parenthetical statement that he was doing peripheral physics, but it was irrelevant because he was in the time-sharing mode at the moment. Subsequent to that, Norm had worked in Menlo Park for IBM on a machine that was originally to have been built in '71, a 500 MIP single processor superscalar machine. That design had become more like 200 MIPS with the effort that was mentioned in projected production costs. Norm went on to timeshare to do an operating system in TimeNet, and in 1985, he and Leroy Tyne started QLogic to exploit a capability-based operating system that started within timeshare. Today, Norm is working with Memex, a new company that plans to apply that operating system technology and hypertext system to certain vertical markets. To his left, next is Chuck Lee. In 1963, Chuck was the head of the H group within the physics department at Lawrence Livermore. The group consisted of about a dozen people working on various aspects of computational fluid dynamics. His own work at the time was with a global atmospheric model written in assembly language and running on LARC being the Livermore Advanced Research Computer. In 1968, Chuck left Livermore and went to NCAR, the National Center for Atmospheric Research in Boulder, Colorado, where he became more deeply involved in turbulent research and weather and climate modeling. At NCAR, he was for some years the director of the division within which weather and climate modeling research was carried out. In '83, Chuck returned to Lawrence Livermore to work primarily on turbulence problems. He retired from the laboratory at the end of 1990, but has been continuing his work at Livermore on turbulence simulation on massively parallel computers. And to my far left is George Michael. 1963, George was working on physics code, doing nuclear design. He collaborated with Norm Hardy on the initial specification for the Octopus time-sharing system that at the time they thought was a resource-sharing environment. He worked on mass storage designs and some hardware acquisitions aimed at high-speed services, including printing graphics with input and output. In 1968, George went for a year to teach and establish a cooperative computer center at Haverford, and the sophomore colleges, the so-called triangle, research triangle, North Carolina. Is that correct, George? And other than that, he spent his professional career at the lab. He did return shortly thereafter, and he's been in high-speed computing. He helped establish SIGGRAPH and the IEEE Mass Storage Technical Committee. He also has retired from Livermore, but is still connected with the lab and is attempting to record the verbal history of the past 30 years of the computation department and to get the lab to use its multidisciplinary expertise in the very large-scale research and development projects for advanced biological and medical studies. Myself, John Ranaletti, in 1963, I was a much younger systems programmer working on the LARC CDC 1604 and 3600s in preparation for the oncoming first, quote, supercomputer, 6600. My expertise at that time was in Fortran IO and Fortran compilers. 1970, I left the lab to work briefly for BBC, Berkeley Computer Corporation in Berkeley, and then I moved from there to Control Data Research Group, which is just down the road here, off of the street there, shortly near here. And then after 2 years on the outside, I returned to Livermore, where I worked on IO support for the Octopus network. Spent 16 years in management, and now I'm going back to full-time research. My interest is understanding English text with various algorithms. What I thought we'd do today is I give a sort of a short slide introduction to kind of set the stage for what Livermore looked like on the floor in '63. Each of my colleagues will speak in turn about their area of activity. Norm will start out with sort of what operating systems were like and what we needed to do to get the jobs done. And then Chuck will follow about how we handled the job, what production was like 30 years ago. And George, who's been in cleanup for us, will do the peripheral and all the extra stuff, except to get visualization started in 1963. Due to the size of the audience, if we certainly have the time, and if you want to interact, please do so. It might make some interesting discussions. After we've made our first pass through, we're going to have kind of a dialogue, and we certainly would like to include you in that. Okay, I'll start with the slides. The first slide is not meant to be read. It's the important thing are the horizontal colored lines, and I will describe best I can. The intent behind the machines. What you have here is 1952 on through to the, it's about 1980, and the horizontal lines show the lifetime of machines at Livermore. The slide itself is historical in the sense that it only goes up through the CDC star. It does not include any of the Cray research computers. We start with Univac 1, which we normally have a power ratio we call 1, normalized to that. And we go down the line through the 701, 704 series, 709, 7030, the Avian stretch, go Univac Lark, the 7090s, 7094, 3600, 7094s, 3600s, 6600s, 7600s, and the star. Now, important things to note the lines, the longevity of the machines. It illustrates a couple of things. They're color-coded by manufacturer, Remington Rand being green, blue being IBM, red being Control Data on this chart. Every machine beyond this point on down, except these two, are Seymour Cray machines. The technologies you'll see in the next slide was changing quite rapidly, so the duration in which we held computers was short relative to the later time frames because the performance increase from years to year was much shorter. In fact, one of these machines, this 7600 serial 1 that we have, which is this one right here, ended up being with us for 17 years. Now, let's look at 1963. This is the vertical stripe that you see. This is the year of our reflection. And it's a year of transition. You're seeing 7090s going out the door, 7094s coming in. You see 3600s coming in preparation for the 6600, which was, for us, a big step forward. Did an interesting calculation. If you take and you add up all these machines this year, their central memory bit size, the core memory size, you add it all up, the total is 2 megabytes. Now, those of you that have used a Macintosh these days can't do much with 2 megabytes. And we ran the entire laboratory with 9 computers or more on that one memory.
It was like 63 was quite a transition.
Yes, it was. If you look at the chart, it was a transition year. We had on the floor some vacuum tubes that was part of the LARP, lots of transistors, and some integrated circuits coming in the middle. So it was a good transition. This is a performance curve just to give you an idea. We started at the bottom in 1952. In 1952, we go across in time, and then we go up logarithmically. And each year it shows the boost in power. And now the blue curve shows a doubling each year of power. And the next blue year is a doubling every 3 years, and then a doubling every 4 years in capability.
That compute power and not power consumption?
Yes, good point. No, that's compute power. And you can see, in the early years, we got significant incremental, and this corresponds then to the less incremental increase due to the arrival of new machines, and therefore they kept them longer.
Well, question on the last view graph, actually.
Sure.
What was the, how many UNIVAC 1s equals 7,600?
Okay.
What was the factor on it?
The 7,600 is considered to be 5,000 UNIVAC 1s. The star is 10,000 UNIVAC 1s. The multiply speed on the UNIVAC lark, which is right here, turns out it was listed as 2,000 microseconds. Notice it said 2,000 microseconds, 2 milliseconds. And 7094 had a multiplier of basically 200 times faster. So you can see in a short period of time, we got a significant increase. And with Sun 3s rated at a megaflop, you can see the corresponding performance difference today. All right. This next slide is basically capital investment. The red lines show the undepreciated cost of computers, and the blue line is the depreciated cost factoring in various life cycle costs and other things. And you can see not only did the performance go up, but also the cost did as well. In 1963, the budget for the computation department in Livermore was $7 million a year. And today it's about $96 million. Okay, here we have first a little historical review. This is the 70. It's a 7090. And since I'm concentrating now around the window of time from 1963, we basically are going to show you very quickly what the machine room floors look like. This is the 7094, which was the successor to the 7090. There's, of course, the card readers. Those of you in the field at the time realized that that was a center of sociability. Often there to wait your time. And in fact, I have this theory that personal communications has suffered because of time sharing in the remote offices, because there are parts of our existence where we used to center around things. We often centered around card readers. We then often centered around localized teletypes. Now we don't have that sociability opportunity. Here's the printer that chugged along and gave us the results.
What kind of characters per second did you get on that?
George?
The printer was 150 lines a minute. If the lines weren't too long.
80 column override, I believe.
So, how many characters per second?
120, actually it's 132, but we only used 120.
And it was also card reader punch, so it also was output too.
You didn't print them both at once.
And of course, there was tape drives, lots and lots of tape drives. Now this, for those of you who've been in the field a long time, this is kind of how we worked. And basically, you did the thing on paper. You then wrote it out on column sheets for the key punchers. You then got back a printout. Notice advanced programming, since there were no go-tos, also there's no comments. The cycle sort of looked like this. In 63, you did the coding, paper, key punch operator, the key punch programmer takes the card file of the operator, peripheral computer puts it on tape, operator takes it, puts it on the production computer, writes an output tape, operator takes it back to the printer, gives it to the programmer, makes a modification, recycle. Average turnaround time, half a day. Average turnaround time, half a day if you missed the left print. And therefore, it was a frustrating thing. And one of the reasons you would increase the production capability of the computer, but it was until time sharing came along, we didn't do much for the turnaround time. When you got here, you found the missing left parenthesis faster, which was the cycle. Yes.
How long on average then did it make sense to inspect by eye, as opposed to just shove out the cards and give it a spin and see when it spins back?
Well, my personal experience is I did a fair amount of inspection by eye, trying to balance the parentheses at least so that I wouldn't get a stupid return. It was frustrating to submit at 8 to come back at 1 in the afternoon to find out if I had a syntax error. Whereas in fact, I really just wanted to make sure I could get the first cycle of numbers right.
So you spend like an hour or 2 hours and then give it a spin?
I think it varied, but I would probably be lucky to get 2 shots a day. And I think probably Chuck will speak to that when he gets the applications, yes.
Back in that same era at Northwestern and IIT in Midwest, they actually had a printer and card reader dedicated just to doing listings. So you could do the check out by hand, not waiting the whole time going through the process.
That's an excellent point. For the purposes of the viewing audience, later, the point was made that often installations would dedicate card readers to printers just so you could have a viewing option ahead of time.
So it was.
What was your budget for paper?
We had a printer that ran through $600 of paper in an hour.
That was 50,000 line a minute.
30,000.
30,000.
Okay, now we're up to the LARC. That's a Livermore Advanced Research Computer. It was built for us at the time when we needed more capability. And that's the famous drums. There were 6 or 8 of these things. They were about the size of the stage. Rumbling, you really had a feel of power when you moved that. Moving on, there's the just lost the stretch. I mentioned earlier about the vacuum tubes. A little bit more advanced research computer that had LARC was the last machine we had before that had any vacuum tubes in it. But primarily, it had most of the circuitry done with transistors. The point about the stretch in the LARC is that it illustrated a period of time in the U.S. government where laboratories could buy machines before they were really developed, sort of a fly before you buy philosophy. And one of the roles the laboratory played in those years was to help industry start with computers. I didn't mention on the first graph, but every machine on the graph, except for the UNIVAC and one other, were virtually serial ones. And so Livermore had a role to play at the time, and that was to help small and large companies. But there's the stretch. Never since the stretch have we had more impressive looking machine. When the press used to come in, they would always gravitate to that and take pictures of this. This is actually a maintenance console, rather than the console from which you operated the machine. Subsequent to this, the only glossy thing we could show is that people with tape drives rotating.
John, can you say where that machine is now?
That machine, I believe, is in the garage.
Isn't that the low lot?
Yeah, that's the low wood, I believe, has that machine in his garage.
Roll for gold.
That's quite a bit of gold.
Yeah.
I'm having trouble with my slide. Is it me or is it?
Lost one slide.
And there's the actual console that they ran the machine from on the stretch. Far less impressive. Notice the ever-present tapes. We move on to the 3600. We had 2 of those. They were bridge machines. We basically got those in order to get to 6600. The 48-bit word, the claim to fame on the 3600 was that it had a register, called a deep register, shift register, that was directly attached to a speaker, so you basically could play music with the machine. And the operators often did. They were off hours. Technology, view of the boards. There's some of them are out there, you notice. 6600 was the focus in 1963. This was serial 1. It was coming into us for the first time, and it was the challenge to bring both hardware and software at Livermore together. 63 was the transition year where we got really serious about Fortran. We wrote Fortrans in the late 50s. A lot of production codes were assembly code through the mid-60s. With the advent of the 6600, Fortran became really a age. More tape drives, card readers, everything else. Discs. Technology. Seymour and Cray's genius is in packaging. And, 6600 is transistor logic. And he put together, this thing was hand wired on the floor at the time wires varying in length from a few inches to several feet. When in fact the machine wasn't timed right, it would take a half inch or so off the wire and do it out to the machine. It really became a uniquely wired machine because so much attention was put on it in the early days. There's the display console. Had 10 PPUs and a central processor, and the status of all 11 machines were visible on this cathode ray tube. This was the beginning of time sharing. Norm's going to talk about this, but this was data at 110 baud. And it was our beginning connecting relatively low-cost machines into the center, and he'll explain how we did that. There were some peripheral machines. There's the 650, 2,000-word machine. That's the one I learned my programming skills on. Again, another video of the 650. 1401 was the machine that did card to tape for us. That's where all the queuing of people lined up. We all became very familiar with 1401. There's the card reader. Also got very familiar with the insides of the card reader. We often had to pull the scribble ones out. This is the 160A, a desktop machine, about the size of the machine Norm was sitting at, or a table Norm was sitting at. It was a machine that basically allowed us to go card to paper tape, and allow us then to then start machines like the 1604 and 3600. So with that, just quickly show another view of the 16. This here is the PB1. George Michael will be talking about that. It's eyeball effects. There's a color version of the same machine. Here's the eyeball again. George will be talking about that. And this is the PB6. This machine was instrumental because he was our first real attempt at centralizing storage. This handled all the network traffic and the messages and storage between our various machines on the floor in the last part of the 60s. More?
Sure. Well, question? Yes. 1963 was significant for the delivery of the 6600 in your time frame or your view?
Yeah, it was significant to us for the purposes of today for a couple of reasons. It was 30 years ago. Nice thing to talk about. It was added at time sharing at Livermore. It was the, I think, turning corner for us into supercomputing, as we call supercomputing today. I mean, you can define any machine at any given time as a supercomputer. It's the fastest one around. But the concept of having multiple application codes running on a single processor by many users started in '63.
I wanted to start out with a comparison. In the beginning of '63, I don't remember the exact dates, but the biggest machine we had was the Stretch, which you saw the picture of there. It's instructive to compare it with a 486 laptop computer. The Stretch had 3/4 of a megabyte. The laptop probably has 4 or 8 megabytes. It had the Stretch was a little bit slower at doing floating point arithmetic than the 486 and quite a bit slower at doing ordinary instructions. It seldom did instruction much faster than a microsecond. It had 32 megabytes of disk. The laptop may have 80 or 120 megabytes. And about the only point at which the Stretch was faster, it could read the disk faster, which was important because the large application codes were conceived to keep their data there and to process against the disk. The Stretch did have a printer, card reader, card punch, and many tape drives. None of those could be lifted by one person, and few of them could be lifted by two. And the Stretch would fill, well, perhaps not fill this room, but you couldn't get two in here. The 46, the laptop computer also has a floppy drive which has about 1/20th the capacity of a reel of tape. And of course the Stretch had no display. Oh, and the other interesting thing, the Stretch consumed about 100 kilowatts. Machines at Livermore for many years all consumed about 100 kilowatts, 120 or so. I think some of the recent Cray machines may consume somewhat more, but they're all in that ballpark. So the power constant from about 55 on has been fairly constant per the largest machine. The 6600 was coming, or had just arrived, and on that machine, the programmer or the compiler was expected to place a few instructions after a load, but before using the value loaded. Thus, it was that, which is my definition of a RISC computer, where they put the burden on the programmer to arrange the instructions to fit the hardware to run fast. It worked very well, and the Stretch had a clock cycle. The clock was 300 nanoseconds. The 6600 had a 100 nanosecond clock, and you could issue in bursts one instruction per clock cycle. You could seldom maintain that. Sounds very much like today's RISC machines. The Stretch had 250,000 transistors. The 6600 had 600,000. And the instruction set for the Stretch was comparable maybe to a 68K in complexity. The instruction set for the 6600 would fit in my shirt pocket, the complete definition of the instruction set. It was a very simple machine to program. My effort was to push time sharing on the 6600. I did have the great good fortune to go back and use Project Mac's CTSS, Compatible Time Sharing System, at MIT just a few months earlier. It had just become stable, and they invited a number of people to come back. I met Gene Amdahl. He was in the next office, also sitting at a terminal running this, learning how time sharing might serve. The time sharing was still widely regarded as visionary and suspect. The official purpose for supporting the labs, the official purpose for the lab supporting the development of time sharing was to improve the efficiency of the development of the physics development teams, those working on weapons. And we sort of viewed the computer as part of such a team. The computer was often as expensive or more expensive than the people. And so we looked at it as a tool to make the pair more cost effective. Before, it would often be the case that a production job would run for several hours, only to discover later that very near the beginning of that calculation, something had gone wrong and the rest had been wasted. So allowing a physicist to watch the computation proceed was a technique of getting the answer sooner and using less computer power to do so. That was the official reason. We were all bigots, and if we would have found some other reason to do time sharing if that one hadn't flown. But that was one of the official reasons, as I recall. So during the day, there would be some production jobs running and a lot of development. At night, the more trusted long-running computational jobs would be running, plus a few nocturnal physicists watching their computations proceed. The time-sharing system was written by 4 programmers and an administrator. The administrator did a little bit of coding too. And it was done, if my memory recalls, in about a little bit over a year. We had projected a much shorter time than that, but in retrospect that seems quite reasonable. You saw the pictures of the teletypes, which were the user interface. They were noisy, heavy, but very reliable. And the specs fit on one sheet of paper. I like things that I can understand all at once. And I like the teletypes for that, although they were annoying sometimes. The system, as we programmed them, it was hard. No one was building interfaces between teletypes and computers that were anywhere near reasonable. And so we found that we had to write programs to deal with the individual bits of all of each bit of each character for all of the teletypes. But all of this fit in one of the peripheral processing units quite comfortably. Such techniques carried over into TimeNet about 9 years later. There was one thing I will mention about the structure of the time-sharing system. It was fairly standard, although it did have forks. A program could cause another program in another address space to start up and run and pretend that it was sitting at the console of that new program. So the first program could essentially control the second program very much as a user could control the first program. This gave us quite a bit of flexibility.
I'm sorry, what was that again? What year was that?
The
Forking process.
The fork. It was not as general as Unix, but a program could initiate another program running in a separate address space. It could initiate one of them, and while the latter was running, the former would not be.
Yes.
But control could come back to the former, and for a pseudo-teletype style interaction.
Yes, about what time was that? What year?
Oh, well, 1960, well, it was certainly running in the middle of 64, and I believe it may have been running in 63.
Thank you.
I see a patent, someone's worrying about patents, so are we. There was one other novel thing. There was a priority system. A user could set his priority, and a user had a bank account that was maintained by the machine. And as his program ran, his bank account would be deducted, would decrease in proportion to his priority. He could set the priority at whatever he wanted, and the system would run the highest priority. And there was a system of incentives that I believe worked very well. You always hear people who don't have enough money complaining, and certainly enough, this was the case as well. The bank accounts were established in regards, well, administratively, and naturally time brokers arose. There was a small political structure that arose, not necessarily politics in the bad sense of the word, but a political structure to administer sort of a financial flow structure that people would trade time. A user could transfer some of his time to someone else, so it was negotiable. I'm getting a little bit ahead, but not much. The physics problems were highly geometrical. How am I doing on time? I haven't been watching. Okay. The physics problems were highly geometrical in nature, and we developed... Are you going to talk about the TMDS? Okay, I think I won't talk about that. And I'm sure you could talk about the movies. The movies, the graphical output. I don't think it. I will make one other comment. It was only later, when I left Livermore, that I realized in retrospect that we'd had a unusually good set of electrical engineers putting all of this stuff together. I didn't realize that some laboratories or some institutions wouldn't have things like this. We had fine electronics engineers that glued this stuff together magically, and as we're having as much fun as we were putting it together and making it work. So that'll do it.
You said there were 4 people working on this project. How could you divide that up so that you could sort of each take a piece of it?
The PPUs, the peripheral processing units, made it very clear that you must separate your programs at well-defined interfaces. And so each of those programs would be written by one person. We had 2 programmers working on code that ran in the mainframe, and no one besides those 2 knew where the divisions were. And since that worked, I don't think anyone besides those 2 to this day knew how that code was organized.
What language, what debugging facilities did you have?
The debugging facilities were, when one of the PPUs would stop, you would have to restart the entire machine. You could find the contents of all the memories. The program counter was not displayed, however.
How do you guess at it?
Well, the hardware had a peculiar quirk, and that is when you hit the reset button, it would stop in the refresh cycle, and that instruction would almost certainly be 0.
Well, undocumented feature.
Yes, that was a discovered feature by the programmers. Debugging the CPU was much more. Oh, the language that the PPUs were all written in assembler. The part of the operating system that ran in the mainframe was written in a set of about 5 or 6 macros. I was very surprised, but almost every line of code these were macros of the form: fetch this field from that area, from that structure. We would now say that fetch that field out of the structure, add or subtract something from it, test and branch.
Well, see, if my memory is correct, CDC had this policy of supplying only hardware, not software. So, that's correct. So you would have, and you had serial number 1.
Right. They supplied a first-rate Fortran compiler. That was about it. Of the code that we used.
There's an interesting comment on software for the early machines. As Norm said, the GOB system was written in a series of macros, a very small number of different macros. Shortly after the proof of principle worked, and as people were wooed into the new environment, there was a rewrite where we actually rewrote it in our extended Fortran. Because we had the challenge of taking physics codes and running them efficiently on the new hardware without much vendor-supplied software, we added pointer statements to Fortran and put structure statements to allow them to get at the bytes within the machine. Anyway, the whole GOB system was recoded in an extended Fortran, and it turned out that, one, it ran a little slower, but it was a lot smaller because the compiler was able to do the memory management, whereas the macros were individualized and did not use any sort of cross-memory reduction. Chuck?
I'm, I think, representing a user, application, a particular application.
You want to put the mic on so that it'll get on tape?
Can you hear me?
But it won't go on the videotape.
Oh. Okay, let me go over here.
We'll work your slides for you.
No, I'll work. The particular application that I was working on in 1963 was an atmospheric model, one of the earliest models of the global atmosphere. It was running on the Lark computer. The Lark was delivered around late 60, early 61, and started to get running, and that's when I got this particular model running, but even in 63 I was still using it. This particular model divided the global atmosphere up into a mesh horizontally of 5 degrees in latitude and longitude, roughly speaking, and described the vertical structure of the atmosphere with 5 layers. So that was that was the nature of the resolution of such a thing. The program was written in assembly language. In that year, as has already been mentioned, Fortran was sort of coming along, but I was unwilling to wait the year or two for Fortran to be reliable on this particular machine. After a machine was delivered, then especially the first machine of its kind, as this was, then there would be some period of time before, in fact, the compiler was put together in a reliable way. Meanwhile, I was using the machine happily. In fact, my feeling about Fortran in those years was that if it was an important program, I would write it, a big, important program, I'd write it in assembly language. If it was something small that I didn't care much about, I'd write it in Fortran. The other aspect of this was, as is so often the case when we had relatively small memories, the Lark memory was 30,000 words, effectively the core memory, that you would write essentially out-of-core programs. The amount of data that was involved in an atmospheric model could by no means fit into that kind of a memory, so in fact you'd have to use working I.O. processes to the rotating drum, a picture of which you saw earlier. In fact, it was laid out in this particular case so that one turn around the drum, one band, corresponded to one latitude in the atmospheric model, and you could watch the head progress from latitude to latitude as you swept from one pole to the other in the calculation. And then I did it in such a way that instead of moving way back, I would reverse the direction, so it would go from south to north and then from north to south. The problem, of course, with doing that is that you had to worry about a relative balance between the I.O. and the arithmetic. So, and in particular, then be sure that you laid out a system in which you were not effectively I.O. bound, but you were, well, you could afford to balance them equally because, in fact, these were buffered. You could be reading in and writing out at the same time that you were carrying out the calculation. So, you hoped usually that you were effectively, the time that you was taking was set by the amount of arithmetic that you had to do. I think when I think back about this time, these times 30 years ago, and when I talk to other people about it, they think of this as kind of a heroic age where people had to write in assembly language and they had to lay out the data carefully and they had to handle all the I.O. carefully and all the rest of it. I want to show you a result from that calculation. I found just today, I found in some old, I don't keep 30-year-old records. I did find a reprint of something which had an image in it, which was taken from this atmospheric model. Because at this time we started making maps from the computer of the field. So one above shows you the surface pressure at a particular instant in time within the model in the northern hemisphere of polar projection. And one of the bottom shows the surface precipitation at that same time. Precipitation to the surface. Note that the dotted contours correspond to low pressure areas, and you can see in the North Atlantic there a storm. It's a winter time, actually, it's January. Simulated January. And you can see in the bottom the rain band or pattern, precipitation pattern, which is associated with this. But you can see it's all relatively crude, but not too bad for 30 years ago. This frame was just one that, in fact, later we turned into color motion picture strips to watch the evolution of this thing. And George Michael had a lot to do with the beginning of that kind of color time-lapse motion picture of the results of the calculation. It was really quite impressive as soon as we started getting that motion The color was used for distinguishing different fields so that you can superimpose one contour in red, another contour in yellow, another contour in red, and watch the way they were moving together. In this particular case, these are essentially single black and white frames of different single fields. Those, I should say, in that year, 1963, I was one of those nighttime physicists that Norman referred to. He was another. George was another. The three of us would finally get tired about 3 a.m. or so, 4 a.m. It seems to me to go have some breakfast at a nearby roadhouse before going home to sleep. But it was during this kind of an interaction in the middle of the night in which you could, in fact, we had a lot of discussions what the future of computing was going to be, many of which I think turned out to be reasonably accurate 30 years later. In particular, we had quite a bit of discussion of massively parallel computing and how we thought that might go. All right, 30 years later, I think to some extent I find myself back in doing the same sort of thing I was doing 30 years ago, but on massively parallel computers, faced with some of the same problems. The languages are not really using the machines very efficiently yet, although presumably within a few years they might do that. The compiler people and the systems people and the compiler people in particular, or the language people I should say more generally, try to keep me away from the hardware as much as they can, or interpose themselves between me and the hardware in a way that I don't fully appreciate. Because they don't yet know how to use the hardware very efficiently, especially, I therefore am in use of parallel hardware. I'm a message passer. That means that I'm finding myself doing something which looks very much like the working I/O that I did 30 years ago, because I have to worry now, instead of sending a message to the future and receiving one from the past, I'm sending one to an adjacent node or adjacent part, adjacent piece of the mesh that I'm working on, and receiving it from adjacent ones. But otherwise, the rules of the game are almost exactly the same so far as I can tell. You launch the write-read process as soon as possible, and you check that it's completed as late as possible. You go on. We did that 30 years ago, and we're still doing it. And the other aspect has to do with essentially with this business of assembly language that I was using before to get close to the hardware. There's still a problem. The biggest problem that I'm having in connection with using massively parallel computers is not communicating information from one node to another, but using the nodes efficiently. The microprocessors that we have now have fantastic rates of doing arithmetic, but they don't have fantastic rates of loading the vector registers necessarily. And the bottleneck is turning out to be between the local memory and the microprocessors in many cases. It's a rather difficult, what I call the cash flow problem, which is one that I'm particularly concerned about right now for a particular architecture. So, as I say, I think that to some extent we have some of the same problems of trying to, at least for now, get close to the machine to find out how the hardware works and use it directly. And from what we learned from that, presumably then people can maybe more sensibly try to put together efficient automatic ways of doing the same thing through higher level languages. But I think this just represents the fact that for many decades I believe there's been what I like to think of as creative tension between the computational scientists, such as myself, and the computer scientist who wants to help me, but is not always very helpful. So.
Yeah, Joe. Oh, sorry. Question?
The question is, are you aware of any programs from 30 years ago that are still running today?
Oh, yes, absolutely.
There are descendants, clearly, of programs which have been moved from generation to generation of computer. The trouble is that they now, if they took a reasonably long time to run 30 years ago, they run instantaneously now. So the tendency is for people to make things more complicated. I have mostly been involved in fluid dynamics calculations, and what has really happened there is one goes originally from one-dimensional calculations to two-dimensional calculations to three-dimensional calculations. What I showed was a sort of a 2.5-dimensional calculation already, but that was considered massive in those years. It's even now a full three-dimensional fluid flow calculation, which I'm interested in for turbulence simulations, can be as massive as you want, depending on how much resolution you put into it. It can absorb any amount of computing power. That's why, in fact, I'm right now so much interested in extracting as much power as I can out of parallel architectures.
George?
You got this, George. No, come on, read this. Good evening or afternoon. I did some thinking about what is history and why am I talking about it. And to illustrate my dilemma, I want to tell you a very short little story. You're all familiar with the cartoon Peanuts that's done so well by Charles Schulz. In one of them, Charlie Brown is saying to Linus, you know, when my grandfather was a little boy, on St. Nicholas's Day, they would hang their stockings, and if they were considered bad little boys, they'd get coal in their stockings. Something to that effect. And Linus said, gee, that's neat. That's swell. That's great. What's coal? Okay. That's our problem here. History is a story of something that maybe didn't really happen, written by somebody who really wasn't there, and he gets to rewrite it, and he's a survivor more than necessarily an historian. But I think there is a benefit in history, and it is that we get to point out, perhaps, some interesting research lines in this case that could be carried on now as they have not been, and point out some errors that you might want to avoid, though each generation loves to make its own errors. You know, take the case of Nikola Tesla. His biography is full of ideas that people should be exploring this day just as fresh as they were when he was alive. And I want to say one other thing. There's such a rich trove of things to talk about. I can't do it justice in a short time chronologically. I've broken it up into three things. One is related to the thing that motivated most of us most of the time. That was the octopus. And responding to the needs of persons like Chuck, who had real problems they wanted to do and needed to get their answers back to them in a timely way and so forth. Okay. Another thing that I was going to talk about was our adventuring with, you might say, personal computers in a sense. We called it a romper room. Okay, it was built around a PDP-1, and if we get to time, I'll show you some of that. And then the third thing was our adventuring in the whole discipline, if you dare call it that, of graphics. Okay, both input and output. So, on to the octopus, and do we have a, let's see, which one of these? This one? All right. This is just machinery, and the thing is not very interesting until you animate it with software. And that's a thing that lots of people seem to forget. But what we had here were a couple of DD60 consoles and a DD80 console. The DD80 was an incredible adventure to us. We're dealing with some very, very slow graphics devices. In 1956, we made so-called the first movies. In 1957, we made the first color movies, and they were made with the help of a device called the IBM 740 on an IBM 704. This machinery which is a cathode ray tube with a very low-grade camera, was produced for IBM by Stromberg Carlson. And we used it and made some movies with it and things like that. We put a better camera on it, but it took 151 microseconds to draw a line. It took 50 microseconds to draw 1 point, and that's all it could do. Draw a horizontal, vertical, or diagonal line, or plot 1 point. Well, that stimulated people, and we had to find ways to provide that utility to lots of people. And that was one of the goals that was present in everybody's mind as we evolved the Octopus. The Octopus, in the personal sense, had an interesting start. It started with Norman. As we were walking out the gate, Norman's walking backwards. Typically, that's what he does because he's so fast, he's ahead of everybody, and he's turning around and he says, I don't see how we can use the stretch to full advantage unless we find out what multi-programming is. And everybody said, what's multi-programming? So he explained that to us, and we read a report that had been produced at Yorktown about the possibility of doing multi-programming or something like it on the stretch. And I think all of us concluded pretty quickly that that wasn't going to work for Livermore. We began there designing what got to be called the initial Octopus, and it has the following interesting characteristics. The Octopus was a device for sharing resources. These resources were all over the place, and one of the things that was going to tie everything together is a very large disk that I believe was being proposed by Burroughs or Memorex. Which one was it? Anyway, it had over 7,700 heads on it. And the idea was that all the machines in our stable that we called physics machines would be able to read anywhere on those 7,700 heads, but they would have just a selected bunch that they could write on. And then a boss that would organize the resources would write messages from one machine to another and deposit them and then poke the machine and say, that's where it is, go read it. That was one of the interesting things in the Octopus. The other one was that on a trip Norman and I made to look at some graphical input devices, we met a guy by the name of Arthur Holt from the Rabenau Engineering Company in Washington, and he told us about a tape idea that he had, and basically it said, we'll take these audio tapes because they're cheap, and audio tape transports because they're cheap, and we will put those into a configuration so that you can read or write them at any speed, and you can move them forward or reverse. And then Norman came up with the idea, well, we'll solve the differential equations for the acceleration of these things, and we'll start them up till we get them to their normal speed, but we can be writing all the way, or reading all the way, as the case may be. The idea was that we would have a lot of these tapes, and it got to be called the basement tape system, and there were 1,000 tapes in the thing, and each tape had the capacity of about 10 to the 8th bits. Therefore, in 1960, we were talking about a 10 to the 11th bit memory that would be available as a resource in the Octopus. Okay. That was the talking about it. In the actual bidding on the thing, the engineers at Rabenau got conservative, and they cut everything by a factor of 4 except the price, which they raised by a factor of 4. So we lost interest in the basement tape. But having been thrown out of Sid's office a couple times for advocating the Octopus idea, eventually Sid even bought the idea, and we started to work on it, and Norman told you how the adventure of the software. He didn't tell you the whole story, though. That's not fair. The software was called GOB, okay? This stood for Generous Omnipotent Benefactor. And someone, I think maybe Norman, pointed out that it was also Russian, backwards Russian for the word for God. Okay, so everybody thought that was a great idea, and it had these macros and so forth. I want to give you numbers for these things. The DD60s were each with a 512 raster. The DD80 in the middle had a 1024 raster, and it was fast, okay? The slowest character you could plot on a thing was 10 microseconds, and it was a whole character, and it was calligraphic, and it looked pretty. And the lines, you could draw any line from anywhere to anywhere, and average in speed from somewhere between 0 microseconds to 6 microseconds. Now that's a comfortable speed. And when we get a little bit further, I will show you. This is the calligraphic characters that we're talking about here. We tried silly experiments like a boat floating across one tube and going into the next one to annoy the operators, but they were too sharp. They did it themselves, okay? We tried looking at these tubes as stereo. We had to be too far back to see them, though. This is a picture of a thing we call the Hardy Hydro. This is the DD80 console. It's showing essentially a 10 by 10 zone hydrodynamics calculation, a simple one but complete. Okay, it would run at the equivalent rate of 30 frames a second. 30 frames a second. Okay, that's nice, comfortable speed, and with it we can service a lot of people in this Octopus. Here's a picture of the other part of the DD80. I will point out what I think is a substantial difference between Livermore, and which I think has obscenely large problems, and normal people who have ordinary problems. These, now those magazines there, that's all right, I don't need it. The magazines are 1,000-foot magazines. The camera is a 30 frame per second camera, pin registered, and the tube, you see all those little things around it? That was this crazy engineer from Data Display who came out, and rather than correct the power supplies to give us a square raster, he glued magnets to the face of the tube, and it would straighten out the raster so it was nice and square. We could measure it to within a 10,000th of an inch with an optical instrument, and it produced microfilm and movies and all that sort of thing, and it was an integral part of the Octopus, and people liked it, okay? We found ways to substitute for that too, but I think that's upside down, isn't it? I don't know what it is.
This is their copy flow.
Oh, it's the copy flow?
Yeah. It's a stacker there.
I don't recognize that. The point is, once you've got film, you need hard copy. The copy flow was a device built by Xerox Haloid Corporation. That's nice, we're in their auditorium, huh? That produced a little over 60 pages a minute, okay, from microfilm. This is a picture of the radiation printer which replaced it. This thing was a real machine. It took the abuse of tons of people and tons of output. The machine's characteristics: it works from this web-fed roll, which is nothing but carbon with a white paint on it, and then into the print head where the stylide burned through the paint in a dot structure, line after microline, to give you characters, and then it comes through a folder and comes out onto this feed belt at 7 pages a second. Okay. Now, it drops a little lower than that because you have to get through the perforations and the fanfold marks and stuff like that, so it's a little less than 7 pages a second. But with it, its volume crept up to approximately 30 to 36 million pages a year. It never went above that because we found that many of the users preferred to have microfiche, which were produced by a set of recorders that I don't have here because they're from an era that's past 1963. This is another picture of the radiation printer again. Radiation was Radiation Incorporated from Melbourne, Florida, okay? And sort of as a weird little machine. The styli were embedded in a plastic, and it was just one line of them, and they would be firing, you know, at the rate that they had to be in order to get this thing. It was a 60 characters per second, and they had to clean it with walnut powder. Ground up walnut shells would be blown against the styli so that you could keep the thing clean. The radiation printer induced in lots of people a kind of allergic reaction, which some people were equipped with a little fan on their desk so it would blow the fumes away from them as they were trying to read this stuff. The favorite name for the output that this thing produced was scunge.
One of the byproducts of working in that particular point in time is that when you went home, from fingertips to elbow was black, because you would lean against the reverse side of the carbon paper, it would rub off.
I'm sorry that this is so dark. I will just have...
George, on radiation printer, is it also true, if I remember correctly, or it's apocryphal, that the perforating station had two separate dies for the top and bottom of the page, and if they got slightly out of alignment, and it's looking like these trick notepads that were spiral?
Yes.
Right? One of the things I was interested in from the early 50s until I gave up was the question of 3 dimensions. I tried it on the DD60s and I wasn't satisfied with it. This is a gadget. It's essentially a bell housing, and I think you can see even in this poor light that there's a 3-dimensional wave shape in there, okay? This thing is a spinning phosphor disc, and it's coated, so not coated, but it's fixed with an angular position indicator so that the computer knows where the disk is at any instant. And when it is busy sweeping out a volume of phosphor, a spherical volume, so all you have to do is wait until you get to that point and then blast it, okay? And you find a lot of tricky things that you know that if you're on this point now, you'll be at the next point that you want to be at in a few fractions of a millisecond or microsecond, and then you fire that, and so you get these pictures like this. This was produced by a guy by the name of Robert Ketchpel at the Hughes Research Laboratories in Malibu, based on some arguments that we'd had, and he had a lovely shop down there so he could produce this thing. We brought it up to Livermore and we showed it to everybody, but it didn't have the sales force that it needed. I'll get to this thing here. When we were making color movies, what it amounted to was to separate the things that you wanted in each color and then to make a black and white strip of just those things for each color. So you would end up with all the stuff in green in one frame, and all the stuff in blue in another frame, and all the stuff that had to be in red in yet a third frame. Or if you had the luxury, you could do all the stuff that you had to have in green down for 1,000 frames, followed by blue for 1,000 frames. Then the question is, how do you put it together? Enter the world's first optical effects printer at Livermore, okay? It's a piece of surplus aluminum I-beam, and essentially nothing more than a camera and a projector, and a light source in the middle, and then a place where you can insert any number of filters. So you can control the projector, saying that I want it to expose one frame and then skip 3, and expose one frame and skip 3. You go all the way down the film that way. Since the film's all pin registered, there are no accumulated errors of any perception. So it worked, okay? This is what we called the optical effects printer number 1. It was built by the help of Dave Dixon in the technical photography group at the lab. Then we got more sophisticated and bought this thing, which does essentially the same thing, but it has more bells and whistles on it, and the technicians liked it better, okay? So it's called an Oxbury, And we bought it from this company in Long Island. You can mount any number of rolls of film on this thing, and by clever optical rotating of mirrors and filters and intensity variations in the light, munge all that stuff onto one frame of in the camera. And this is largely still the best way for making very high quality movies in color, though we've added in later years, in the 70s, we've added tubes with genuine white phosphor and a set of filters so that you could photograph in color film immediately. You lose a little bit in resolution and you lose a little bit in speed, but it no longer seems to be very important to be high resolution or high speed. This is where we did all of our analysis. It's called a Vanguard. It's a pin-registered gadget, very important, and we could make measurements on there and then translate those measurements to the optical effects printer. Okay, here's the PDP-1, our romper room. I want to skip through this quickly. It had a tube. It had a typewriter. It had a handset for audio input. It had speakers for audio output. Okay, there are many other things that I'll try to touch on really quickly. This just looks at the console. You could talk into it. We tried experiments of talking into the computer and then having it clean up the voice, and then we would play it back, and it was thought that, well, you could do this for blind people. You could do this for operators who were not near a console to be able to read on a teletype or on a screen, and the machine would say, move that tape. People didn't like that either. Anyway, but it was nice. We had high fidelity output on the thing. This is 1960, okay? This is the thing that Norman programmed. You wouldn't recognize this unless I told you. That is a keyboard for a musical instrument after Norman finished with it, okay? So you could play, he would go and play Bach on the thing and things like that, and only he seemed to be able to remember where each of the keys was that had to have the right note attached to it. That thing above it, this is what is coal kind of thing, paper tape reader. This is a little bit more interesting. We found that this was a highly well-liked received thing at the lab, the CalComp plotter. It had the ability to move a small distance in X or in Y or in X and Y, okay, anywhere around the thing. And using some algorithms that Norman taught us and stuff like that, we made this thing draw lines, draw artwork and so forth. Yes?
Why did Ken put
I can't hear you.
Why did Ken put a telephone on the PDP-1?
Why do I have the
Why did Ken Olson put a telephone on the PDP-1? What was that for?
Well, it was that this is a way to get voice in.
That was, I mean...
No, that wasn't a option. That was Livermore put the telephone.
Yeah, we were just... I told you, this is our romper room. We tried all kinds of crazy things. One of the things that was a
part of the machine.
Yeah? Oh no, it wasn't a part of the machine from DEC, but we put it on because it was easy to interface and so forth. The PDP-1 was nominally to study the life cycles of devices that we were going to put on the Octopus. We tested IBM Selectrics and ASR-33s or whatever they were then, and I found the ASR-33 was cheaper and more reliable and so forth, and so that was the thing that was being used. And then whenever you had an idea about something you wanted to do on a big machine, you could work it out on here. We had a little, I've forgotten the name of it already, but a little formula translator kind of thing that was equivalent to Mathematica today, only not nearly as exotic, okay? And it would produce pictures for you on the screen, and you could put them into stereo and see what it looked like and say, well, I want to change that. This was one of the things that was our pet hate. That is a Potter tape drive. and everyone hated them. They would hardly ever work. But that was all that was available on the PDB-1 until our engineers, as Norman pointed out, they had a lot of fun doing the stuff to fix this stuff up, okay? When the PDB-1 came in, it had Potters. Yeah. When it left, it had IBM 729 Mod 6s on it, and they worked much better. When the PDB-1 came in, it had an Analyx printer, 600 line in the printer. When it left, it had an IBM 1403 printer. When the PDB-1 came in, it had a beautiful thing called the Uptime card reader. I couldn't find a picture of it, okay? But it was great, okay? It read 2,000 cards a minute, and it produced the most beautiful fountains of cards flying in the air and falling down. And it taught everybody who used it the value of sequence numbering. And we got rid of the Uptime card reader and put a Nancy 2 on it, a 1401 card reader, okay? A little slower, but it was more reliable. Now, this is a RAND tablet down here, okay? It was the first attempt to build a stylus input device, and we had some friends down at RAND, and so they gave us one, and we put it on the PDB-1 to try it out. Above it is just some power supplies which controlled the next thing that I think I've got in the thing. Yes, it controlled the eyeball, okay? The eyeball is the graphical input side of things. You could put film right here, and using this high precision 4K by 4K raster CRT, look to see what was on the film at each point in the space, and to have an idea of what the CRT was producing, we had this section over here as a reference beam. So you would compare the stuff that came through here with the stuff that came through here, and it would tell you what the density of the film was at that little point, 1 of 16 million, okay? That was possible. Now you build up mosaics of responses. I'll show you some of the problem with that because I think it's this is just a close-up of the beam splitter. Here is a picture of a thing that we did lots of from 1959 until essentially they shut down testing. This is called a Rossi trace, named after the guy who thought of this idea. The Rossi trace is made by having a zero amplitude sine wave modulated by a slowly rising ramp in this direction. And by putting the on the vertical plates, a signal that comes from an experiment. And it pulls the thing apart. This allows you a very, very accurate measure of time. This allows a very, very accurate measure of signal strength. This illustrates a problem up here. I'll show you. Come on, you. This is what the eyeball sees. And the simple question is, where the hell did the beam go? So the only way to find that out is to put in the entire idea of what a beam is. Okay? It's essentially a set of electrons being moved at very, very high speed from a gun to hit a cathode ray, to hit the cathode ray tube face. And they're being made to go so fast and at such high intensity that there are two things that happen. You get halation when light is photographed, and the second thing is you get a lot of secondary emission electrons, okay, that hit the electron hits a screen and off some electrons bounce and then they come back. So the question is, where did the beam go? Well, by putting in this dynamics and so forth, you could actually find out where the beam had gone, and that would allow you a more accurate measure of the stuff that the researchers were trying to get at. Now, I thought I had put this in the right place. Oh, that's what those guys were doing out in the Pacific. That's actually not an American shop, though. That's a French shop. I believe they call it Numea. I had thought that I had some other things. I want to mention two other things. We thought that everybody needs a display on his desk. We cannot afford $100,000 PDP-1s, even at Livermore, for everybody's desk. So we came up with the idea of using television, and that was called the TMDS. And the idea of the TMDS was that you would put the video image on some sort of refresh medium that you could afford. Initially, it was a cobalt nickel disc built by Arm & Miller at a place called Datadisc here in the peninsula somewhere. And then you would not transfer, but that head was intimately tied to us to some tube somewhere, maybe through a crossbar switch. And so the guy got to see a noise-free, two-level video picture, and he could react to that through his time-shared terminal. All right, I think I'll quit until people want to start an argument or something.
I think at this point we have some questions from the audience. We've been going for a while, and sure, go ahead.
When did you first use modems, both hardwired and the acoustic coupling?
I didn't hear that.
When did you first use modems?
Oh, the first modems? Norman, you can answer that, can't you?
Let's see.
It'd be pretty late,
1966, 67 were... Now, I had left Livermore, but we used some of the earliest modems. I'm thinking of acoustic modems.
I might make a comment on the modems. There's one out there in a big wooden box that we would put the whole headset of the telephone inside. And I'd like to use this opportunity to thank Barbara Costello and Alice Pitts for bringing some material for all of us to review. As you leave when we're finished, you're welcome to look at it. Any other questions? Comments? Yes.
Back to the issue of modems, it didn't seem to me that were very important because of security reasons, everything was hardwired. And that gets to, I think, a more interesting issue in that it was mentioned earlier that there was a big electronic engineering team that put together all kinds of special gadgetry. In particular, all the crossbar switches that handle the video signals for TMDS and put together the multiplexing electronics that was used for multiplexing all of these teletype lines into the PPU and the 6600 and whatnot. There's some pretty amazing engineering that was done at that time.
Out of necessity. It's in the back.
I was going to ask, on the 6600, when did you start using scope?
I couldn't. Did you hear what he said?
Scope.
Actually, we never used it.
Yeah?
Let me...
When would we use it? When was it first used?
Oh, the DD60s.
I think you mean the operating system. Yeah. We never used scope at Lawrence Livermore. The evolution of operating systems at Livermore, as back to our earlier question about getting serial number ones, for almost the entire decade of the 60s, through the advent of the stars in the early 70s, we developed our own internal operating systems, which were written in Fortran, extended Fortran, which the Fortran compiler was written in extended Fortran. And then since the beginning of the mid-70s to today, we have evolved to commercial software. So on our current machines, we're running from the Cray Research Corporation, we're running their version of Unix. Yes?
On your first slide that you started off the evening with, you showed a graph of a whole bunch of computers with relatively short lifetimes.
Correct.
I wish I was that old, or I'm glad I'm not that old, one of the two. It seems that in transitioning from one computer to the next, you're going to change assembly languages, and if everything is written in native assembler, how much time do you spend reinventing the wheel, translating your program to new assembly languages versus updating the program and doing new and neat things with it?
Chuck? That's a good question for you.
Yeah, I think that that of course was a considerable value of a something like a Fortran language, and along about the mid-60s, in fact, Fortran was compiling loops more efficiently than I could write them in assembly language, and so that's when I started switching over, and I think other people did too. But it also shortened this transfer time to a new computer if the compiler was running on the new computer. That was the other awkward aspect of it. But yes, that was an important aspect of the use of Fortran. That I'm sure was what brought people over. Right. Let me make a comment, however, about the Fortran at Livermore. There was actually delivered with a 6600 computer a Seymour Cray's version, or Garner McCrossan's Fortran. He worked with Seymour Cray, a version of Fortran. Seymour Cray had written the operating system himself, so when he was checking out the machine, I can remember he used both the screwdriver and a pencil because he was worrying both about the operating system and the hardware. But the Fortran compiler that was put together for the purposes of getting that machine going actually turned out to be a very popular one by the users. It was not popular by the systems people who wanted to use the users to check out their Fortran, of course, as is so often the case. So there was a certain amount of, as I mentioned earlier, creative tension within the Livermore Laboratory in connection with the issue of what compilers was the most appropriately one to use on the 6600. Because of the coming of time sharing, we could vote with our fingers as to which compiler we would use. And I think it was kind of interesting to see the dynamics of that. The Fortran people had really to compete with a compiler that was really quite efficient.
Small question, so Seymour's Fortran was written in its own,
Garner McCrossan, who wrote the Fortran for the 6600, essentially wrote it in, not in Fortran.
No, he actually wrote it in Octal. Octal, yeah. Let me go back to that cycle graph I showed on how the program started on paper and went through punch paper cards and then around through tape and then back to the programmer. There's an intermediate step that, for you younger members of the audience, called the binary cards, where we would punch out the actual octal or binary representation of the object code on the binary cards. And then we would resubmit those if you had no changes. In other words, if you just changed the data. But since that cycle was so long, a half a day, we got down to the point in the 60s where we would put the bits back into the holes in the card, and it turns out that they were so clearly punched, you could just stick them back in and they'd stay through the card reading process. So talk about undocumented code. We ran object codes with bits put back in the holes to correct for the thing, because we didn't want to take the half-day cycle. Other questions? Yeah.
To be fair, you actually had a little tape that you used over the holes.
We didn't use tape.
We never trusted it that way. We used tape. Little red tape.
You stick the holes in, then you run reproducing punch and see if they'd stay.
So it's quite a contrast from all the software engineering that we're dealing with today. Any other questions? Okay, seeing none, I thank you for being here. We enjoyed the opportunity to reminisce, and I'd like to thank the panelists and also again Barbara Costello for bringing the stuff, and thank Peter for inviting us.
We're planning to go down after we get everything packed with the panel to the Golden Bish restaurant in downtown Palo Alto, Emerson Street between, I guess, Forest and Hamilton, if anybody wants to come and join us for dinner. Thank you.